Okay, so in today's lesson, we're going to be learning about something called continuity. And as you can assume, continuity just means is something continuous or not. So there's a couple things that you need to kind of have an understanding of. And first of all, that's where you're continuous at a point C. All this means is that there's no interruption of the graph at point C. So if it's continuous at a point, then there's no interruption at that point. Secondly, if it's continuous on an open interval, that means that the graph is continuous at every point within that interval. So you can be continuous at a point, and then to be continuous on an interval is to be continuous at every single point in there, which basically means there's no interruption within the whole interval. So that's what we're going to start out talking about. The first tab is continuity. And if we look here, this is the mathematical definition. It says a function f is continuous at C, and C is a point, if the following three conditions are met. So all three of these conditions have to be met in order for a function to be continuous at a point C. So you can kind of think of this as like your checklist to see if f is continuous at C. All right, so here they are. F of C is defined. That means that whenever you try to evaluate this function at C, there's actually like an answer. It's not undefined, it's defined. So here's an example of when f of C is not defined. And we're going to kind of look at this graphically. So here's our interval from A to B, and there's a point C. And so say we have a straight line, but there's a hole at C. Well, then that means that f of C is not defined because there's no y value that matches up with that C. The second one is that the limit of f of x exists as x approaches C. So that means you have to be able to find a limit. If the limit does not exist, then you can't have the function continuous at C. So here's a graphical look at a limit that does not exist. So you're going from A to B. Here's point C. And you've got something looking like this. So the first criteria is actually satisfied because f of C is defined. It's this point up here. But when you try to find the limit of f of x as x approaches C, and you use your fingers, you can see that it doesn't approach the same value. So it doesn't meet the second criteria. Now the third one is a comparison between steps 1 and 2. So not only does the limit have to exist, but it says here the limit has to equal f of C. So these two have to equal each other in order for the point or the function to be continuous at C. So here's an example where that doesn't happen, where the limit of f of x as x approaches C does not equal f of C. Again, we've got our interval from A to B, C's in the middle here, and say you have something like this. That's supposed to be an open circle. Open circle. And then you have a point right here. Okay, so does f of C exist? Is it defined? Yes, it's right there. Does the limit exist as you approach C? Yes, it does. However, the limit is a different number than f of c, which means it's not continuous. And if you just look at these, it's kind of a no-brainer. If you have a graphical representation, you can tell that, oh, there's an interruption at that point, so it's not continuous. But that's just the mathematical rigorous definition that I want you to understand, and you are going to be tested on understanding this mathematical definition. So unlike some of the last lesson 39 where there were all these formulas and I told you you really don't need to know them, you need to know this definition of continuity. And you need to know that these are examples, or non-examples rather, of when these criteria are not met. Okay, so I know this is a long video, but now we're going to discuss the continuity of each of these functions. And whenever I say discuss, like I might on the test, that word implies that you need to ensure all three conditions are met. So when I say all three conditions, I'm talking about these conditions over here. So now I'm going to grab my highlighter. I'm going to highlight those three conditions. And I'm going to highlight the word discuss and ensure all three conditions are met. Because if you don't understand what that word means, you will not get this correct on the test. So y equals sine of x. We're going to try to do this hold up. This is the definition for f if it's continuous at c. Oh, so it has to be continuous at all points. So here, when we're discussing the continuity, we're now shifting our attention from just one point C to thinking about all the points C within an interval. And for this interval, it's actually from negative infinity to infinity, since there was no specification. So, first criteria, does f of c exist for all values in this interval? So can we plug in any value x and get a y value that matches it? Yes, because it's just an oscillating function that goes on forever. There are no holes, no jumps, no gaps. So f of c is defined for all x values in the domain. And that's just one like that you have to understand. There's no jumps, there's no holes, there's no gaps. So if I had more room, I would also kind of include that in my discussion here. So step 2, or condition 2 rather, is that the limit f of x exists. So the only time that a limit would not exist is if, like in this example, you're approaching from two different values, or if you had an asymptote, like we learned about not that long ago, unbounded behavior, like this, or if you had like a crazy sine function where you had something like 1 over x, so that the graph is going crazy. But we don't have that here. We don't have any asymptotes, any jumps. We already said that up here. So that same logic applies to step 2. So the limit of f of x as x approaches c exists for all values of c. That's another way of saying all x values in the domain. And now our third criteria, it says that the limit of f of x as x approaches c is equal to f of c. Well, if you think about this sine function, there's no reason for that not to be true. We haven't found any jump gaps, asymptotes. There's nothing here that would hinder us from plugging in any x value. And if there aren't any jump gaps or anything that looks like this on the graph, then the third one is also satisfied. So I'm going to put here that the limit of f of x as x approaches c equals f of c for all values of c. And I could discuss that a little further. I could say that this limit would be evaluated using direct substitution, and this function would be evaluated using direct substitution. So it makes sense that both the limit and the function would be equal. And we're done. So we've discussed the continuity. This function is continuous everywhere on the sine curve. So now let's talk about this one, because this one is not going to work out. So the first criteria isn't met. Well, what is it? It says f of c is defined. So is the function defined for every value negative infinity to infinity? Or are there some kind of asymptotes or jumps? Well, it looks like it's defined for everything because we have a greater than symbol here and a less than or equal to symbol here. So it's encompassing all the values of x. So yes, f of c is defined. Just like you see above, f of c is defined for all values. In order for it to be undefined, you would have to have a restricted value of some kind, which here we don't. Now let's check number 2. It says the limit of f of x as x approaches c exists. Well, wait a second. Okay, for this one, we probably need to kind of sketch out a graph because it says the limit of f of x exists. The place in question is right around this 0. So we need to figure out what's happening right here. Is there a jump of some kind, or are they attached? So I'm going to draw a little coordinate grid right here. And we're going to test out x values -1, 0, and 1. So if we plug in -1 to here, because it says less than or equal to 0, then we're going to get 0. So -1, 0 right there. And when we plug in 0, that's also part of the top part. So we have 0 plus 1, which is 1. So we have some kind of line that's looking a little bit like that. Now we skip to a number that's just a little bit bigger than 0. So let's do something like 0.1. Okay, so pretend we're plugging in 0.1. 0.1 squared is like 0.01. So this is 0.01 plus 1. So it's just a little bit above the point we're already at. So we can actually assume that this is going to be something like that. And that means that they actually do approach the same value whenever you're talking about limits, and there's no gap here. Like, it doesn't appear that the limit wouldn't exist for any reason. So we can say that the limit does exist. I'm not going to repeat all that stuff. And then 3, this is the one I was concerned about. I thought it didn't work, but it actually does. The third one says the limit has to equal the function evaluated at that point C. But it looks like the limit at 0 still equals 1, just like f of 0 equals 1. So that was the only point that was questionable, and it turns out that the limit of f of x as x approaches 0 is equal to f of 0, which was the only point in question. So far, all of this is just really mathematically dense. It's just a lot of reasoning about things that probably kind of seem common sense. So tomorrow in class, we're going to analyze some functions that these conditions aren't true. Okay? And now let's move on to the bottom half.